Welcome to Understand Chemistry. I am Dr. Bilal, and in this video we will continue our exploration of free radical polymerization. In my last videos I have explained in detail the monomers and initiators used for radical polymerization and how initiator efficiency is reduced by cage effect. In the last part of video I have raised a question: how to avoid self-initiation. In this video you will have a detailed understanding of inhibitors and retarders and how they control self-initiation and polymerization. Inhibitors are the substances that suppress the polymerization. These substances act by reaction with the initiating and propagating radicals, converting them to their non-radical species or radicals of that much low reactivity that they cannot undergo propagation. They are intentionally added to the monomer for the purpose of storage to avoid self-polymerization. Sometimes they are added to the reaction as scavenger to stop the polymerization. Retarders are less efficient and stop only a portion of the radicals. In this case, polymerization occurs but at very slow rate. Substances such as benzoquinone, nitrobenzene and nitrosobenzene are the famous examples that can act as inhibitors and retarders. To better understand how they work, let us have a look at this plot. The figure shows effects in the thermal polymerization of styrene. The black curve is for the reaction where no inhibitors was used. This is over baseline. The polymerization proceeds rapidly, reaching over high conversion with no interference. In this reaction, free radicals drive the reaction efficiently. In the red curve, where 0.1% benzoquinone was used, exhibits an induction period. This means polymerization does not start until benzoquinone is consumed, after which it follows the same path as the black curve. The blue curve, where 0.5% nitrobenzene, which is a retarder, is used, polymerization begins immediately but progresses at a constant low rate. The green curve, where nitrosobenzene is used, first inhibits polymerization, then converts to nitrobenzene, which acts as a retarder once the inhibition period ends. Now let us see an important parameter that helps us to quantify the strength of an inhibitor. This is called inhibition constant and is defined as the ratio of rate constant of inhibition reaction to the rate constant of polymerization. Remember, since initiation and termination happens once for a chain and most of the reaction in polymerization is propagation, that is why the rate of polymerization means rate of propagation. For a strong inhibition, the value of Z is much greater than 1, or we can say Kz is very big than Kp. This is valid until inhibitor concentration is significantly reduced. Actually, the effectiveness of initiators is dependent on several factors such as monomer radicals, kinetics of the reaction, and temperature sensitivity. This means one inhibitor cannot be equally effective for all types of monomers. A compound can act as inhibitor for one monomer but can act as retarder for other monomer. Here is a table depicting different type of combination of inhibitors, monomer and corresponding Z values. Let us take one example from the table to see which inhibition is better for a monomer. Let's say for styrene. We see different possible system of styrene from table but can clearly see that oxygen is best inhibitor for styrene. Let us see some example of inhibitor and how they act. Oxygen is a powerful inhibitor. Oxygen reacts with radical to form relatively unreactive peroxy radicals that reacts with itself or another propagating radical by coupling or by disproportionation reaction to form inactive product. Quinones such as 1,4-benzoquinone and chloranyl are the classical example of inhibitors. There are two possibilities of attack of growing polymer chain on the benzoquinone molecule. One is oxygen and other is on carbon of the benzoquinone. Let us consider the case when Mn radical attack the oxygen. As a result of this, a allyloxy radical will form, which can terminate by coupling or by a disproportionation reaction with other propagating radical. In the second route, when the attack of the propagating radical happens on the carbon of the benzoquinone, a new radical is formed. One possibility is that this radical will rearrange itself to yield another radical that can terminate by a reaction with other radical, or it react with other growing chain terminate by a disproportionation. Aromatic nitro compounds terminate propagating chain with a great effect for more reactive and electron-rich radicals. Nitro compounds inhibit vinyl acetate, retard styrene, but have a little effect on methyl acrylate. The mechanism of radical termination involves attack on both the aromatic ring and on the nitro group. Attack on the aromatic ring yield another radical which reacts with another propagating radical, or it can react with monomer. Attack on the nitro group lead to radical highlighted in yellow, which can react with other propagating radical or cleave to nitrosobenzene and MNO radical. Both nitrosobenzene and MNO radical can react and terminate other propagating radical. Phenol is a poor retarder, but when electron donating group is present, such as a substituted phenol or 2,4,6-trimethylphenol, it becomes a strong retarder. For example, for vinyl acetate, the Z value of phenol is only 0.012, whereas for substituted phenol, the value of Z is 0.5. 2,6-ditertiary 4-methylphenol is another example of substituted phenol that can act as a powerful retarder. Oxidant such as ferric chloride and cupric chloride that can accept electron and convert to ferrous chloride and cuprous chloride in reaction are strong inhibitors. Radical termination by FeCl3 is shown in this reaction scheme. Stable free radicals such as DPPH also inhibits polymerization. Since this radical is strongly colored, its consumption during the inhibition period can be followed photometrically. As I mentioned before, inhibitors are deliberately added to monomer to avoid autoinitiation and self-polymerization. So in order to polymerize them, we have to remove the inhibitor before the reaction. There are several ways to remove the inhibitors. The first method of removing inhibitor is alkaline washing. This is useful for phenolic inhibitor like TBC and hydroquinone. This purification is based on principle that phenolic inhibitors become water soluble as phenoxide ion in basic condition and can be separated out by solvent extraction. Second method of removing inhibitor is distillation. This is widely used method. It is based on the principle that monomer and inhibitors have different boiling points. Styrene has a boiling point of 145 degrees Celsius, whereas the TBC has a boiling point of 285 degrees Celsius. So in this case, styrene can easily be distilled out. Column chromatography is another versatile method to remove inhibitors. In this method, monomer is eluted with some solvent mixture. For example, hexane and ethyl acetate is one of the examples. Using silica or alumina column, inhibitor-free monomers are obtained by evaporating the solvent. Here is a table showing that what type of column material is the best for a combination of monomer and inhibitors. This is all about inhibitors and retarders for radical polymerization. Next, we will explore kinetics and mechanism of radical polymerization. Feel free to post your question in the comment section. Thanks for watching.